Hi everyone, in this video I want to introduce you to some of the important ideas of mathematics that go with music, and particularly in this video, pitch and intervals. Before we get into that, here's 4 quotes. The orange ones are from mathematicians, the green ones are from musicians, and that might just get you thinking about what this all means and how it can be useful. Now, the reason I wanted to do this is because some people have defined music as melody, harmony, and rhythm, but of course it's a bunch of other non-tangible stuff as well. But melody and harmony are all related to pitch, and pitch is about frequency of vibration, and that's all about maths, and that's why we're going to explore this. What I'm going to do is look at the note A, and I'm going to play it on a guitar, which will look like this, or if we break that into pure tone, it looks like this. Now, if I play the A below middle C on my electric guitar, the string vibrates at 220 Hz. Then the magnetic coil pickups here, they sense that, and they turn in an electrical signal, which then goes to a speaker, and the speaker vibrates at 220 Hz. Then a pressure wave goes through the air at 220 Hz, which hits our eardrums, and then our eardrums vibrate at 220 Hz, and which our brain then interprets as an A. All these vibrations look different, but that's physics. We'll just stick to the maths part. Now, the pitch of a stringed instrument is given by this formula. I like this formula because the only number in it is a 2, which is nice and easy. Or, sorry, a half. Making it nice and easy. So the frequency is a function of the length of the string, the tension of the string, and the density of the string. Now, you can change the tension but it's not real good to do that during playing. You can change the density by playing a different string. But what I'm really interested in now in this rest of this presentation is changing the length. But let's just quickly look at the A string. The length of it is 62.8 centimeters. The tension is about 80.5 newtons when it's tuned properly, and the density of this particular string that I have is that. And when you put that in the formula, you get 110 Hz. So, that second string there is the A string, and it's 628 millimeters long, and it vibrates at 110 Hz. Now, if I cut that string in half, or I put my finger halfway down here, this is also the note A, and it's 220 Hz. If I cut that in half again up to 440 Hz, I will get another A. I don't have space on the fretboard to actually make a decent sound of it, but I will get another A. Okay, so anywhere you press those frets there on those particular strings, you'll get the note A. And you'll see that each time the frequency is doubled. That's called an octave. So the lowest one, A here, is an octave below this A, which is an octave below this A, which is an octave below that A. Okay, so that's all the A's that you can do on your guitar. Now, on another string, this point here will give you an A, but if you chop that length in half, you also get another A the octave above. So this idea of halving the length will double the pitch, giving you an octave above, works on every string there. So I've talked about octaves. So if we've got our lowest A, looks like that, the octave above will be moving twice as fast. So in the time that the low A does one period, like going from the middle to the top to the bottom and back to the middle, the next A will do that twice. The next A will do that 4 times. And the next A will do it 8 times. So when you go up an octave, the period halves, or you have twice as many in the same time, which is what this shows. In 1/100th of a second, for the lowest A, you get 1 cycle, 1 period. But for the next A, you get 2. For the next one, you get the yellow one, you get 4, and the red one, you get 8. So there's the A's. So the octave is probably the most important interval in Western music, but in most music around the world, another really common interval is the perfect fifth. So you can see here that it's not doubled, it's 1.5 times. So 1.5 times 440 is 660. 1.5 times 220 is 330. It's called the perfect fifth because in the major scale, the E is the 5th note there. 1, 2, 3, 4, 5. In the chromatic scale, this is 7th note along. Anyway, when you draw them together, it looks like that. So in the time that the A does 1 cycle, the E does 1.5 cycles. Just to confirm what we said before, if you got 1.5 times the frequency, perfect fifth, it's 2/3 the length. So there's the A, there's the E, it's 2/3 the length, so 1.5 times the frequency. And that works the same on any string. Now if we add them together, we get this black pattern here, because if you take that blue one and that pink one, at that point add them together, you get that black one. If you take that pink one and that blue one, that's positive and that's negative, so when you add them together you get 0. So this is what, when you play the two notes A and E together, this is what you hear. And it looks like a nice repeating pattern like that. If we superimpose that with the original A, you'll see that it does its cycle in the time that A does 2 of its cycles. So you kind of hear some interesting patterns there when you play the two notes together. Okay, the final thing I want to talk about is, yes, we know that going from A to E is a perfect fifth, but going from E to the next A is called a perfect fourth. Fifth because it's the 5th note of the scale, and then you go up another 4 notes of the scale to get to the octave. So A to E is a 5th, E to A is a 4th. Now this means some interesting things with our fractions, because, yeah, 2/3 the distance will get you to the 1.5 times frequency, so that's your 5th. But if you compare these two distances here, you got 3/4 of the distance will give you 4/3 the frequency. And look, then we got from your 110 to your 220. So your little fractions there work out nicely. So the perfect fifth is 2/3 the length, 3/2 the frequency. The perfect fourth is 3/4 the length, 4/3 the frequency. It works on the open string, but it works on other strings as well. Same fractions there. So in summary, from A to A, you've got an octave that's half the length, twice the frequency. From A to E, that's a perfect fifth, 2/3 the length, 3 times the frequency. From E to A, that's perfect fourth, that's 3/4 the length, 4/3 the frequency. And if you look at the other intervals, you'll get some equally as interesting fractions. So this is just an intro to a lot of this stuff, guys. So keep exploring music, keep exploring maths, and good luck with that. All the best.